Some warm-up exercises. 4 springs each have an unstretched length of 10 centimeters. When the masses are hung from the springs, they stretch as shown. Which spring has the largest spring constant? Which has the smallest spring constant? Talk to your neighbors about this. And in about 30 seconds, I'm going to call a name out of the box and ask you which one has the largest, which has the smallest, and how did you determine that based on the information on the slide. Talk to your neighbors. Let's work this through. The spring constant, it tells us how stiff the spring is. And if that's going to determine how much it stretches. Okay, right here, I have a mass of 100 grams, and I attach it to the spring. How much does the spring stretch by? I mean, it had a length of 10 centimeters, and it stretches to a length of 15 centimeters. So how much has it stretched by? 5 centimeters. Okay, now I double the weight. I double the weight from 100 grams to 200 grams. It goes from 10 centimeters to 20 centimeters. How much has it stretched by? 10. Oh, so I've doubled the length. I'm sorry, I've doubled the weight, and I've doubled the stretch. Okay, now 10 centimeters, and if I stick 300 grams on it, 3 times as much weight, how much does the spring stretch? 15. Oh, triple the weight, triple the stretch. So in each case, to determine the spring constant, we're doing it like this. Force is equal to k times x. And if I have a weight of 100 grams, it stretches by 5 centimeters, 200 grams, 10 centimeters, 300 grams, 15 centimeters, 400 grams, 20 centimeters. What's that tell me about the value of k for each case? Same. It's the same value of k. These are basically identical springs. And if I have more mass, it stretches farther. Okay? Okay, given that, think about that. The springs are identical, but the masses are different. So given that, what can we say about the second piece? If the masses are subsequently raised a short distance and then released, which mass will oscillate with the highest frequency? Talk to your neighbors about that. I'll call a name out of the box to speak to that one. Which one oscillates with the highest frequency? The lightest one. The lightest one will have the highest frequency. It'll have the highest frequency, the shortest period of the oscillation. It's because the mass is smallest. So you're right. And actually, physically, that makes a great deal of sense. Let's think about this. We'll come back to the hamster here. I have a spring, and if I suspend a small mass from it, okay, it'll oscillate. And what's providing the restoring force is the spring, okay? The spring is providing a restoring force. Well, if I take that mass and I increase it, there's the same spring which is providing the restoring force, but it's applying the restoring force to a much bigger mass. And so we'd anticipate that it's going to have a smaller acceleration. I raise it a small amount and let it go. And then what happens is it just oscillates at a lower frequency. Why? There's more mass. There's more inertia in the system. And so it takes longer. Okay, so Rachel's just right on that. Now remember that, because we have a puzzle problem that we'll see later in the class that relates to that. But let's take a look at this one, a pendulum problem. If I take 5 masses and suspend them from strings to make pendulums, as shown, which of these pendulums will oscillate with the highest frequency? Talk to your neighbors about that, and I'll call a name out of the box to tell us what the answer is and why. what determines the frequency of a pendulum? The length. And which is going to oscillate more quickly? A short pendulum or a long pendulum? The short one. Now there's two short pendulums here. There's A and E. What's different between those two? The mass. Does the mass make a difference? A and E are the two that you have. These two are tied for having the highest frequency. The lowest frequency, of course, would be this one. It would be the longest one. But the mass doesn't make any difference.